Hello and welcome to Physics Problems One by One.
So here is a problem. As always, read it, maybe once, maybe twice, and then pause the video and try to solve it yourself.
Today's problem is part 3 about unweighting up and unweighting down during skiing. Previous part 2, I gave you like a quality analysis of the situation, why one unweighting is preferable than another. And today I will give you a little bit more quantitative analysis of the same. I was discussing trends and ideas last time, and I didn't wrote a lot of formulas. Today I will try to address it using a little bit more formulas and more numbers in the end, and this will prove the same result, but it will be more detailed than what we did last time. So basically the model is, let's start with unweighting down. Unweighting down. So in unweighting down we have the skier who pulls up the heels of his boots towards his butt. And what happens here, let's assume that there are flexors, muscles, that pull the lower part of your body up. And I will put this lower body as M lowercase. And this would be my first case, unweighting down. This is when the skier sits down, or what is absolutely the same, pulls his heels towards the butt. And the lower body is M, it's probably 20% of the body. And the upper body is, I will call it M capital. And all of this happens as this is mg, the gravity is acting on the lower part of his body. And then the F, this is the force of his flexor muscles, because there are two kinds of muscles in every limb. One is extender and another is flexor. So obviously extender works to extend the limb, and flexor, the opposite one, works to flex it back. But I assume that it would be the same force that acts during unweighting up and unweighting down. So this is unweighting down, and the force is from the upper body, and it pulls the lower body up. And of course there is also surface, and this surface acts with N. And of course similar case would be with M uppercase, which is upper body. But the formulas that we can write here, let's put the X down, and we will write the sum of all forces equal MA in the vector form. And if we will project straight everything along one line, and everything goes down, so we can see mg minus F and minus N, and then as a normal reaction from the snow that we want to eliminate equals MA. We can say that our goal is when N equals 0. N equals 0, that means we disconnected from the snow and we can initiate the turn. Snow doesn't affect us at all, and that actually means that MA, I put it this way, equals mg minus F, right? And then it's gone and everything, and then assume we have to make an estimate. So we will make an estimate that the force acting in this case and the next scenario, which is unweighting up, it would be the same. And let's assume that acceleration that we have, acceleration is equal to g, this is assumption. It may be g into 3, g over 4, but doesn't really matter. We assume that the body, this m, it still accelerates down at that point, and accelerate with acceleration g. So the upper part of the body goes down with acceleration g, and of course it's not g, it's all on the incline, so it's not a g, but there would be sine alpha component, as we see from the problems in this playlist a little bit later down the road. But for my estimate, it doesn't matter. Those coefficients, they're not so important. Besides those coefficients, sine alpha, it would be the same for unweighting up and unweighting down. So in both cases, I make similar assumptions. So I assume that f is the same, and I assume that a equals g over 2 when unweighting down. When unweighting down, this is this acceleration. And if I plug it here, I can see, and let me do it a little bit differently. I say a equal g minus f divided over m. This is my acceleration. And I like this formula because I will be using it in the next case scenario. And then I say, let's assume that a equals g over t, or g divided in 2, sorry, and this would be 1, of course. 1 minus fm. And this immediately I can plug it here, and this will give me immediately result from here that f equal mg over t. So I assume that this force, this assumption that there is force and that resultant acceleration is g over t immediately leads me to the fact that f equal mg over t. Of course, that's very reasonable. I take half the weight, half mg, half the gravity. Half the gravity of mg with my force F that I'm pulling my upper body up, and of course my acceleration is decreased in half. So if I, let's say my body is 20% of my weight, and I pull it up with the half of the weight, it's pretty reasonable. It's nothing exceptionally strong here is required. And if I pull it up, I already have acceleration of lower part of my body, g over t. And that's very important. And the next step that I want to calculate time, how fast this is happening, and compare all of this with unweighting up. So during my movement, the upper body moves down, it's falling with gt squared over 2. This is the distance that the upper part of my body is going down. But my lower part is going with at squared over 2, because acceleration is significantly less. And that means that upper body, the torso, goes down more than this because g is more than a, right? And I can say that this distance is d. This distance is my compression. So I lift my upper body for the d, and notice I keep everywhere lowercase, and d is gt squared minus at squared. And I can say immediately that 2d, and I don't want even to plug here a equal, not yet, a equal g over t, but I get 2d over g minus a equals t squared. Or I get that t equals square root of 2d g minus a. And this is a formula. So I can plug into this formula the numbers right away. Let's say that I pull my body very little. I need very little to pull my body. Well, I don't know, 4 centimeters, for example. Let's plug this number. So let's plug it right here. T equals square root of 2, and there is 4 centimeters. Let's say 4, 10 minus 2. because it's centimeters and we do everything in meters. And G minus A, it's 10, 10 divided in 2, it would be 5. So it would be square root 8 over 5, square root of 3, and square root of 5, it would be 2, roughly 2.1, and this would be not 3 but 2.8, so it would be 2.7 divided over 2.1, 10 minus 1. Well, it would be something like approximately 0, it would be 1.5, 10 minus 1. So it would be 0.15 seconds. It's very rough estimate, and of course you can get it much better. But I can say the time that it will take, and I will put it here, time that it will take in real numbers would be very roughly 0.15 seconds for initiation of the turn. It's reasonable. It's 1/10 of a second or 2/10 of a second to lift my lower body up and complete the initiation and turn from one turning left to turning right. Very reasonable and makes a lot of sense. So t equals 0.15 seconds. Now let's deal with the situation when we're doing unweighting up. It would be very similar, but we have two motions here. First motion, we're sitting, we compress, and then we expand, and we expand, and we expand, and while we're expanding, we're pushing down on the snow. And it's only when we expand completely can we continue a little bit and lose the connection to the snow. And this would be exactly the same moment when we start a free fall, and during this free fall we initiate the turn. So we completely expand, and so we have to cover, first of all, we have to push with F and N, and it would be M capital. And the force down would be M capital. Everything would be the same, only it would be M capital, right? And this would be M capital, 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 and this would be M capital. And I'm assuming that I am, let me not make it dirty, but I'm assuming that from this formula, I will rewrite it. This would be again the same, and this would be acceleration capital, So let me wipe it out and do this cleanly. So M capital, M capital, M capital, M capital, and I can say A capital. A capital is acceleration when I am weighting up. It would be, if I divide everything into M, I will have M here, I have G here, and I have minus F over M. And if I take G, factor it out, it would be G1 minus F over mg. And now here I can get this acceleration providing I am using the same force, because I have to compare apples to apples. So what would be acceleration of my body if I am using the same force of my muscles, only my muscles now, not flexors, but extenders, how they call them, I forgot the word. Flexors versus extenders. So those extenders work with the same force, so I will get A equal G1 minus, and instead of this I put this, and it would be mg divided over mg, and there would be 2 in the bottom. And in this case, let's put it A equal G, 1 minus, and it would be M over M big 2. And I can assume, let me keep this because I will need it for in 2 seconds, but I will wipe it here because it's the same formula, second law of motion, and that's n equals 0. And I have M is 20% and then big is 80% of my body. So if I plug those numbers here, I will get A equal G, 1 minus 1/8. Or A equal G, 7/8 G. So that's very interesting result right there. If I'm using the same force, and this is the same force whether I'm moving down or up, so I wipe it out from here. So because the mass of my lower body is significantly 4 times lower, the acceleration that I'm falling down, in this case of the lower body, is g over 2, and here it's 7/8 g, so it's almost double the acceleration. So because the same force acts now against the mass of the upper body, right? And it makes no sense, right? So this is exactly like this. All right, so and now let's go to the same formula, about the distance. Only distance would be, when I'm unweighting up, would be d capital, because everything is bigger. G t capital 2. This is how much the center of mass will fall down. Minus a capital t squared over 2. And so this would be the same formula, 2d g minus a capital equals t squared, and automatically I will receive t equals square root of 2d g minus a. And I can put it here, I can put it like this, and I can say that t capital equals square root of t d capital g minus a, where a is this acceleration. So that's fantastic, because now I can forget about all of this and I can compare one over another. I can divide time t over t, and I will have this divided over this, and this would be square root of d capital over d lowercase, multiply on square root, this would be g minus a, and this would be g minus a capital, if I'm not mistaken. I think I'm not. So now if we plug the real numbers, first of all this part is acceleration, and if this number is g minus I, it would be square root of g over 2 divided on square root of g over 8, because g minus a, 7/8, 1/8, it would be g over 8, and it's right away will be a square root of 8 over 2, square root of 4, it would be 2. So it would be immediately t over t equals 2 square root of d over d. So two things, remember in the previous part I was talking, one part is this is acceleration. The same force produces quite a bit of acceleration when it acts on small body and significantly small acceleration when it acts on bigger body. Because this is just not the full acceleration, it's just compensation for some part of gravity. So it accelerates significantly less, and this is 2. And another thing, d over d. D capital over d lowercase. And d uppercase maybe like half a meter. You just really expand from sitting down really seriously up and you almost jump. So if this would be a square root of d over d, it would be, so let's continue, 2 square root, and let's put here 50 centimeters. And here we will put 4 centimeters. To be as before, we can put, doesn't matter. And I don't even have to convert to meters, because I can multiply 10 minus 1 and centimeters, 10 minus 2 and 10 minus 2, and they will all go away, because as long as both are centimeters, it doesn't matter. And the end result would be 2 square root of 50 is square root of 12. 12 is roughly 3.5, it would be 7. So I can roughly say that under this t over t is 7 times. And it's very rough estimate, of course. And of course it doesn't takes into account the inclination, the real angle, the friction, the direction of speed, the condition of snow. It's all irrelevant, but it tells us that the time is 7 times shorter when we unweighting down versus our unweighting up. And I didn't took into consideration when I'm unweighting up, I have to do the same motion on top when my acceleration is, when I'm at the apex of the turn, and I didn't took into account when I start to unweight down, I can immediately start turning, so it's maybe, I don't have to wait until my end completely disappears, right? So it's really very, very fascinating result for me, that with such a rough assumptions and very rough model, we still receive a very reasonable end result, that times are so much different, and as in practice it's really the case. Trust me. So yeah, I hope you liked it, and if so, please like and please subscribe, and you will see new notifications. And if you have comment, put it down. If you have a question, write it down. If you have a problem that you want to solve, put it down. And I see you next time. Thank you.